we look again at the same situation. Initial velocity of 35 meters per second in the x direction when we have the 40 meters per second at 30 degrees. Still a drop of 20 meters, but we're not going to care about that now, because what we want to do is we want to see what the velocity of the object is at its maximum altitude, at the peak. And we can do that by energy. We could of course do it by the equations of motion. When the ball rises, it starts with an initial velocity of the y velocity is going to be 20 meters per second, and it's going to stop at the top of its arc. The y motion will be 0, the y velocity will be 0, and then we can calculate our change in y and divide that by the acceleration to get the time, and so forth. It's a very straightforward calculation, but let's look at the energy picture. The energy picture tells us that we start with a kinetic energy of 800 meters squared per second squared times big M. Now what we want to know is how much kinetic energy do we have at this point, because if we know the kinetic energy here, we can calculate the loss of kinetic energy, and that's going to be equal to the gain of potential energy. So how are we going to find the kinetic energy? You can see here where we're leading with kinetic energy, but how did we find that? Well, at the maximum height, the y velocity is 0, so all the velocity is in the x direction, and the x velocity doesn't change, so it's going to be equal to the initial x velocity. So if we zoom back just a little bit and move over, we can see that at the maximum altitude, the vector velocity is just in the horizontal direction. It's 35 meters per second in the horizontal direction. In that case, the kinetic energy is just going to be 1/2 mv squared, with big M as the mass again, and we're going to get 612.5 meters squared per second squared times big M. So we start off with this kinetic energy, we end up with this kinetic energy. Our change in kinetic energy is negative 187.5 meters squared per second squared. Another mistake. Got to multiply that by M, don't we? Since our change in potential plus change in kinetic is 0, we can put our change in kinetic in here and get our change in potential very easily. And of course that's going to be plus 187.5 meters squared per second squared times M. Okay? So we know that between here and here, the altitude increases by enough to increase the potential energy by this amount. So now all we got to do is find our delta y between here and here. And how are we going to do that? Well, pretty simple. The change in potential energy between 2 points of a mass m is mg delta y. The weight times the height you got to lift it. So our delta y is going to be our delta potential energy over mg, and we write that expression out like so. Simply change of potential energy is our 187.5 meters squared per second squared times big M. Our big mg is big M times 9.8 meters squared per second squared. We divide that out and we get something like 19 meters. So that this object rises 19 meters from the point where it starts to its peak. And we got that result by energy considerations. We never used an equation of motion. We never used an acceleration, or well, we used a couple of velocities, but none of the vertical velocities, certainly.